All right, my bad.
Are you
Well,
okay?
they'll be able to see this first too here. All right, I'm gonna hit erase now. All right, 3. A client with respiratory alkalosis has an H3O plus concentration equal to 5.76 times 10 to the negative fourth in their blood plasma. What is the pH of the client's blood plasma? So how do we go from H3O plus to pH?
Can't you use the formula
Yeah,
for
so
it? The
pH
pH.
equals the negative log of the concentration of H plus, aka H3O plus. So we type or we plug this in. So into our calculators, the negative log of 5.76 times 10 to the negative fourth. And this one I did pre-solve. I was like jumping around for some reason. pH equals 3.24.
Yeah, I got 3.23.
Okay, so you just matter of rounding a little bit,
Yeah.
which is fine because it's going to be, like I said, it's all multiple choice. So like there shouldn't be any ambiguity in rounding. There won't be answers that are close enough, is what I'm saying.
Yeah, okay.
All right, ready for number 4?
Mm-hmm.
All right, what is the formula of the conjugate base of HCl? So right now this is an acid. To find the conjugate base, it has to lose a proton. So if HCl lost a proton, it would become Cl minus. Any questions there?
It's always wait, why is it negative?
So right at this stage, it's neutral. When it's HCl, it's neutral, it has no charge. It lost a hydrogen. Hydrogen always has a plus charge. So when a solution loses a plus charge, it becomes negative.
Okay.
All right, I'm gonna have to erase before I move on. So, well, I guess if we're recording this, then maybe I won't waste time doing that. All right, erase. All right, so 5, still acid-base stuff. Determine the Bronsted base. Basically, just read this as determine the base. We didn't talk about, there's 2 different ways you can define acids and bases. There's like the Bronsted way and then the Arrhenius way. Doesn't matter. So determine the base on the reactant side, right? So on this side, for the following equation. So we have H2SO4 plus H2O yields H3O plus and HSO4 minus. So I start these problems by trying to figure out what their pair is. So it looks like H2SO4 becomes HSO4 minus H2O becomes H3O plus. So here H2SO4 lost a hydrogen, meaning it's an acid, and H2O gained a hydrogen, so it's acting as a base, it's acting as the acceptor. So if this was to say A, B, C, D, you would choose the one that said H2O. H2O is acting as the base. All right, number 6, calculate the percent weight volume in the units of grams per mil of a solution prepared by dissolving 2.13 grams of sodium chloride and enough water to give 0.3 liters of solution. All right, so this is just part over total times 100. We need to make sure our grams are on top and our milliliters are on bottom, and the problem reminds us that by stating this here. So we want our 2.31 grams on top. We want milliliters on bottom, and we're given 0.34 liters. So 1,000 mils equals 1 liter. So 0.34 liters is like saying 340 mils times 100. And I didn't mean to make this less than 1%. That was a mistake of my part. I don't think you'd have a problem that's less than 1%.
And the unit would be like it would be written like that, like percent. Because
Yeah,
that's what I was confused about when I did it. I didn't know what unit or like what to put with the answer.
yeah, it's a percent, and it might have in parentheses WV after it. But for sure a percent.
Okay.
All right. So 7, a normal saline solution for an IV drip contains 1.12 grams of NaCl per 0.7 liters of solution. What is the molarity of the solution? So you have to be able to recognize that molarity is big M. And remember that big M is moles over liters, which I probably will give you in the reference sheet. So moles over liters. So right now, one of our given values is in liters, but our other given value is in grams. So we need to go from grams to moles. We can do that using the molar mass of NaCl, which is, again, you'd have to calculate this on your periodic table, but for the sake of it here, it's 58.44 grams per mole. So I'm going to start with my given. And I want to get into moles. So I'm going to put my grams on bottom, my moles on top. So that means I'm dividing 1.12 divided by 58.44, and I get 0.0192 moles. So now it's a matter of plugging this number for my moles and then the 0.70 for my liters to get my big M. And when I did that and plugged it into my calculator, I got 0.0274 big M. All right, number 8, this is the partial pressure law. All right, so a gas mixture of neon and argon has a total pressure of 1.7 atmospheres. The partial pressure for neon is 0.89 atmospheres. Calculate the partial pressure for argon. So the total is just the pressure of neon plus argon equals the total. So if our total is 1.7 atmospheres and our, neon is 0.89 atmospheres, we can just treat argon as X, subtract, put an equal sign here, subtract this from both sides. So 1.7 minus 0.89, and we get, where did I put this? Oh,
0.81.
yep. All right, any questions? All right. All right, number 9. I anticipate that this might be a difficult problem because you're looking at this and you see a lot of different numbers. You see big M and you see milliliters, and you might be thinking you might need to do some kind of stoichiometry. But this is a dilution equation problem. And how I want you to be able to identify this is it uses the word dilutes in it, and it gives you three different values. And the dilution equation has four values, so three different values leaves you solving for one value. All right. So remember the dilution equation is C1 V1 equals C2 V2. Given to you on your formula sheet, you just need to identify that this is the problem you would use that formula for. All right. So whenever I have a problem with lots of variables, I always write them all to the side here and kind of identify what's what. So a student dilutes numbers 34.5 mils of a 2.75 molar nitric acid solution. So this must be our starting point. So we have 2.75 molar. We have 34.5 mils. All right. And the big thing with your finishing point is that it needs to be the total volume, the total finishing volume, which this problem is giving us the total volume. It's not saying, oh, I'm adding X amount to it. It's already has the final volume for us. So that's great. We don't have to stress about that. All right. So that leaves us solving for the final concentration 2. All right. I
Well,
just
I could
needed
do.
2
I
more
have to do that
people to
assignment,
weigh.
but
Just to let you know, I am recording, so what you missed, I'll post the recording after this. I'll make it a YouTube link and you can be able to see what you missed, just FYI. All right, so going back to the problem here, this is just a matter of plugging this in and solving. So we have 2.75 for our C1, oh, one more thing. We needed to make sure that our units were the same on both sides. So it needs to be mils on both sides, which it is, and it will come out as molar on the second one here. Our units just need to match. All right, so 2.75 times our V2 or V1, 34.5 equals X times 300.0. So I'm going to divide each side by 300 to get X by itself. And when I did this, I got 0.316 big M. All right, so number 10, I also anticipate that this one will be kind of a hard problem for you guys to identify just because we haven't done a lot of practice of them. So this is an ideal gas law problem. And that is the PV equals nRT formula. All right. So how I know this, right? So one, it's talking about pressure of gas. So it's one of the two gas laws that we learned, either partial pressure or ideal pressure. We already did the example of the partial pressure earlier where it had the word total in it. Here, this one has gas and pressure again, but it's giving me a bunch of different variables. All right. So this is a 5-variable equation, but one of our variables is a constant, and that's R. All right. So it's given me basically 4, and I have to solve for the 5th. So like I did before, I'm going to write all my variables off to the side. So pressure happens to be the thing we're solving for. Volume is 6.75 liters. N is moles, 3.45 moles. R is that constant. This would be given to you. It's 0.0821. And then temperature is 25 C. So with using this ideal gas law equation, you have to be really specific about the units. So the pressure has to be in atmospheres or ATM, which we're solving for it. So it's going to come out in ATM. Volume needs to be in liters, which it is. N needs to be in moles, which it is. R, we don't need to worry about, that's a constant. And, sorry, I'm omitting another person. There we go. And then T has to be in Kelvin. So we have to take this Celsius to Kelvin. So 273 plus Celsius equals Kelvin, which would be a formula you would be given on your reference sheet. So 25 plus 273 is 298 degrees Kelvin. So now I have all my variables and I need to plug it in. So PV equals nRT. So my P is my X, my V is my 6.75, my N is 3.45, my R is that constant value, my T is 298. All right, divide each side by 675 to get X by itself. And we get the pressure is, kind of depending on how you round, 12.5 atmospheres. All right, any questions? All right. So moving on to number 11 and then 12. All right, so 11, a client has a systolic blood pressure of 345 millimeters mercury. Express this in units of ATM. So this is just changing pressure units, which I gave you this like long slide where it was like 1 ATM equals 760 millimeters mercury equals 760 torr equals something something something, right? And we did like one example. So that's like that's this kind of problem. So you'll be given this on your reference sheet. You just need to be able to identify that this is the problem you need to use it on. So we're going to start with our given 345 millimeters mercury. All right, so I want my millimeters mercury on top and my torr, I'm sorry, my millimeters mercury on bottom, so they cancel. My torr, oops, we're not going to torr, we're going to atmospheres on top. So 1 atmosphere equals 760 millimeters mercury. So then it's just a matter of 345 divided by 760, which equals 0.45 atmospheres. All right, number 12. So now we're getting into some of our stoichiometry problems. How do I know that this is a stoichiometry problem? Well, first I see that I'm given an equation, which is like a dead giveaway. I'm also trying to figure out, I'm sorry, I'm going from one substance to another, right? And I can only change substances doing stoichiometry. So I'm trying to figure out how many grams of iron there are from 4 moles of Cl2. So I'm going to start with my given, moles of Cl2. So my given is already in moles, which is great because now I can immediately switch substances. Remember, I have to be in moles in order to switch substances. And I'm going to use those coefficients from the balanced equation, which it's already balanced. I see coefficients there. So I'm going to put moles of Cl2 on bottom because I want them to cancel, and moles of Fe on top because that's my desired unit. So there's 2 moles of Fe for every 3 moles of of Cl2. So now I'm in my desired substance, but I'm not in my desired unit. I want to be in grams. So I need to now go from moles to grams. I know this relationship via the molar mass. So the molar mass of iron, I would have to look up real quick because this isn't one of them that I had pre-solved because, like I said, I was jumping around for some reason. All right, so I'm getting this from the periodic table, 55.84 grams per 1 mole. My handwriting looks really messy over there. All right. So I'm going to put moles of iron on bottom because that's what I'm trying to cancel. Grams of iron on top because that's my desired unit. So for every 1 mole, there's 55.845 grams of iron, right? And I am getting that from the molar mass, aka from the periodic table. All right, so now I type into my calculator 4 times 2 times 55.845 divided by 3. And I gotta do that because, like I said, for some reason I didn't pre-solve this one. All right, so we get 148.9 grams of iron. That is our final answer. All right. And again, for anybody who joined late, I am recording this, so anything that you missed, you can find in the recording, or if I'm going a little too fast, again, you can watch it over in the recording. But please stop and ask me questions now if you have questions. All right. Number 13, we have given the following equation. Determine how many moles of iron chloride are produced from moles of Cl2. All right, so again, stoichiometry. I'm doing stoichiometry because I'm switching substances. I've been given an equation. It's already balanced. So I'm trying to figure out how many moles of FeCl3 are from 0.35 moles of Cl2. So I'll start with my given. And similar to the last problem, I'm starting in moles. Moles is the unit I need to be in to switch substances. So I can start by switching substances by using that mole to mole ratio. I'm going to put moles of Cl2 on bottom and then moles of FeCl3 on top because that's the unit I want to get to. So then I can use the numbers from the balanced equation. So there are 3 moles for every 2 moles, or 3 moles of Cl2 for every 2 moles of FeCl3. So I'm out of moles and I'm into my new desired unit. It just so happens that, I'm sorry, I'm into my new desired substance. Just so happens that that also happens to be the unit I want to be in as well. So I can just stop here. 0.35 times 2 divided by 3. All right. Any questions? All right, so 14, balance the following equation. All right, so when I balance, I always start by getting a count of all the atoms on each side. I like to put a line down the middle and list the atoms, and I like to list them in the same order on each side. All right. And when I do my initial count, I prefer tallies because then I don't have to, if I'm adding a coefficient to something and therefore adding more atoms of something, I don't have to go back and erase. I can just add more tally marks. So I'm starting with 3 carbons, 8 hydrogens, 2 oxygens. On this side, I have 1 carbon, 2 hydrogens, 3 oxygens. So when I was looking at this, my first thought was to add a 3 and get my my carbons balanced first. So adding a 3 here, which will then bring the carbon count to 3 on this side. And the oxygen count, I'm adding 3 times 2, which is 6, plus this guy over here, so 7. All right, so that brings my oxygen count to 7. So I have my carbons balanced. I'm gonna leave my oxygens for last because I see that I have this O2 by itself, which means I can basically manipulate oxygen without manipulating any other elements. And I love when I see that.
You said 7 for oxygen, but you put 8.
My bad. There we go. All right, so next, I think I want to tackle those hydrogens. So I have 8 hydrogens on the left and only 4 on the right. And I can make it 8 by adding a 4 to this guy, to the H2O, which would bring it to 8. But again, that's going to change my oxygen count. So I now have 6 from this guy, and then 4 from here, which now brings our oxygen count to 10. All right, so we have our carbons balanced, we have our hydrogens balanced. We have 10 oxygens on the left, and we can balance it by our oxygen by itself. I'm sorry, 10 oxygens on the right. We can balance oxygen by itself here on the left. So it's O2, so half, if I take half of 10 is 5. So 5 times 2 would equal my 10. All right, so I'm now balanced. I got 3 carbons, 3, 8 hydrogens, 10 oxygens.
You do that again. I'm so confused.
Do it
Like I
again.
get it, but like I got confused trying to copy down and listen to what you're saying.
Yeah, I can do it again. All right. So when I tackle balancing equations, I usually write down a line down the middle and list my atoms, and I like to list them in the exact same order and do an initial count. So initially I have 3 carbons on the left, 1 carbon on the right. I see a chat, and yes, I'm going to send this later. This recording out later. I'll make sure I do it today. All right. I see 8 hydrogens on the left, 2 on the right from this guy here. Oxygens on the left, I just have 2. I just have 2 from this. And then on the right, I have 3. So I have 2 here and 1 here. So 1 plus 2 equals 3. All right, so right now I'm unbalanced because I don't have the same number of carbon on both sides, same number of hydrogen, same number of oxygen. They're all unbalanced and I need to balance them. So when I look at this, I see O2 by itself and I'm thinking, I want to save oxygen for last because when I see an element by itself like that, it's a good one to leave for last because I know when I manipulate it, I'm not manipulating any other elements and therefore causing myself to have to go back and start the count over. So I'm gonna leave oxygen last, and I'm thinking this starting with the carbon. Doesn't matter really if you started with the carbon or the hydrogen, you're probably gonna end up at the same place. I ended up starting with the carbon, trying to make the carbons equal. So in order to do that, I would need to put a coefficient of 3 on the right here. And that changes my carbon count to now 3 on the right. It does alter my oxygen count. So now I'm doing this 3 times this 2 here for an oxygen count of 6 up here, and then still a 1 here. So 1 plus 6, my oxygen count is now 7. All right. Now I'm going to tackle those hydrogens. So on the left, I have 8 hydrogens. On the right, I have 2. If I throw a coefficient of 4 in front of that H2O, that 4 is going to multiply by that 2 and give me 8 hydrogens. So now my hydrogen count is at 8. But I did alter my oxygen count. So this 4 times 1, so now I have 4 from here, and then 3 times 2, so I have 6 over here. 4 plus 6 equals 10. All right, so now I'm at a point where I have my carbons balanced on each side and my hydrogens balanced on each side, but I have 10 oxygens on the right and only 2 on the left. Since oxygen's by itself, like I said, this is a good, easy one to balance because I'm not going to be changing any other elements when I put a coefficient in front of that, meaning I don't have to like go back and make sure everything else is balanced because I altered another element. So this oxygen is coming in a pair of 2 here. So in order to make it 10, I would need to do 5, a coefficient of 5. So that way it's 5 times 2 equals 10. And so now I have my oxygens balanced as well. All right. Any questions?
Okay, so the only question I have is how did you get 10 oxygen on the right? I see the 4. Yeah, I see the 4 because that's for hydrogen and oxygen. Oh, wait, no, you're not adding, you multiplying. Okay, so yeah, can you say that?
Okay. Yep. So there's 4 hydrogens here because, okay, so this 4 would fan out and multiply by the subscript, whatever subscript's on oxygen. There happens to not be one, therefore it's just 4 times 1. 3 would fan out and multiply by the subscript on this oxygen, which happens to be 2. So 3 times 2 is 6. And then I'm adding together the amount of oxygens I got from each compound.
Okay, that makes sense. That makes sense.
All right. All right. All right, 15. A nursing student has a sample of methane gas containing 3.1 times 10 to the 19th molecules. How many moles of CH4 are found in this sample? So I know this is a problem where I'm going to be using Avogadro's number because I see the word molecules, and I remember that we said that 1 mole equals 6.02 times 10 to the 23rd stuff, and we said that stuff, we could fill that in with the word molecules, we could fill it in with the word atoms, particles. I don't remember what else we saw in our vocab, but we can fill that in with words like that. So I'm going to start this problem by starting with my given, which is 3.1 times 10 to the 19th molecules. I'm not switching substances or anything, right? Because I am not given an equation and I see that I'm solving for the same compound, just different units. So it's just a matter of using Avogadro's number to change the unit. So I know that 6.02 times 10 to the 23rd molecules, and I'm putting that on bottom because I want it to cancel, equals 1 mole. So then I put into my calculator 3.1 times 10 to the 19th divided by 6.02 times 10 to the 23rd equals, and when I pre-solved this, I got 5.15 times 10 to the -5th moles. All right, next problem. So 16 is another one that I anticipate might be difficult. So this is one, we only did a few examples of these. We only did a few examples of like all of these because we're just crunched on time, but so a student has 4 moles of CH or C3H8. How many moles of hydrogen are in the sample? So you might be freaking out because you're like, we're switching substances. We're switching from C3H8 to hydrogen. But I'm not given an equation. So how the heck am I supposed to do stoichiometry? Well, you're not. This hydrogen is from the hydrogen in that original compound, C3H8. So we're going to start with our given 4 moles of C3H8. And now we're just trying to get to moles of just hydrogen. So for every 1 mole of the entire compound, I have 8 moles of just hydrogen. And I know this by breaking down the compound. So this compound is made up of 3 carbons and 8 hydrogens. So I just do 4 times 8 divided by 1 gives me 32 moles of hydrogen in the entire compound. I'm sorry, in 32 moles of hydrogen. All right. Seventeen. All right, 17. A student needs 4.5 moles of sodium chloride. Calculate how many grams are needed. Great. So we've already used our knowledge. We know that the relationship between grams and moles is to use the molar mass. I think it gets in scrambled order for you, so I don't know if you'll see this problem before or after you hit those stoichiometry problems, but this is a problem on the exam. All right, so we're starting with 0.45 moles of NaCl. And we're trying to go from moles to grams. That's relationship is the molar mass, mm. Specifically, the molar mass for sodium chloride, which I just have this memorized after years of doing this, but you would go get this from the periodic table, is 58.44 grams per mole. So I'm going to put mole on bottom because I want them to cancel. That leaves me with my 58.44 on top. So now I'm into grams, which is great. That's what the problem wants. So I can stop here and go ahead and do some multiplication. So 0.45 times 58.44. And when I plug this into my calculator, I got 26.3 grams. All right, number 18 comes to us from like lecture 1 when we talked about protons, neutrons, and electrons. This little thing doesn't look perfect like it does on the exam. I had trouble trying to format it on like a Word doc, so I apologize. But what this is really trying to look like is this. I couldn't get this fraction bar to disappear. Anyway, so given this information, we need to determine the number of protons, neutrons, and electrons. So the number of protons is the atomic number, right? So if I went to Br or bromine and looked for it on the periodic table, it would be number 35. That's its atomic number, which also corresponds to the number of protons it has. That number is also just listed in the bottom left corner in this setup. The setup is called a nuclear symbol. Okay. Then our neutrons is our mass number equals protons plus neutrons. So our mass number is in the top right here. All right. So we can solve for it by subtracting our protons from it, since that's what we know we have. So neutrons is going to be mass number minus protons. So 80 minus 35, which is 45. Now, electrons. So if you had no charge here, if it was neutral, your protons would equal your electrons. So no charge, protons would equal electrons. But we have a charge. And so it's charge equals P minus E. So we have a charge of -1. We know we have 35 protons. All right, so to get E by itself, we'll minus 35. Then we have -1 minus 35. You know what? The negatives really confuse me. How I was trying to do it algebraically, but usually in my head, I'm usually looking at this like, okay, what number needs to be here in order for it to be a -1? So 36 would give me a -1.
So it's 35.
I have 36 electrons. The 35 came from the number of protons. All right, any last questions? All right, number 19 is a problem that just basically wants you to solve for the molecular weight, aka molar mass, which you had to do in a bunch of other problems in order to even solve them or attempt them. So I kind of think it's stupid that they ask you this as a question by itself, but it's there. So to find the molar mass of entire compound, you just add together the molar masses of the individual elements, making sure to take into account of how many atoms they have. So from the periodic table, hydrogen is 1.008, but there's 2 atoms of that in H2O. So 2.116. And then oxygen, there's only 1 of them. So just whatever's on the periodic table. Some periodic tables for oxygen will be 15.99, some will be 16. All right, so then we add these together and we get 18.01 grams per mole. Okay, so number 20, this comes back to us from lecture 1 as well. This is converting temperature. So you would be given the formulas, you just got to plug them in, basically. So a temperature reading of 75 degrees is measured on a Fahrenheit thermometer. So aka our given here is 75.1 degrees Fahrenheit. All right. What would this temperature reading be in Kelvin, or what reading would this temperature give in a Kelvin thermometer? All right, so we have to go from Fahrenheit to Kelvin. There's not a formula for that, so we're gonna have to do a 2-stepper where we go from Fahrenheit to Celsius and then Celsius to Kelvin. So the formula for Celsius equals the Fahrenheit minus 32 times 5/9. All right, so 75.1 minus 32 times 5/9. 75. All right, So I got 23.9. All right, and this is Celsius. So we still have to go to Kelvin. So the formula is Kelvin equals 273 plus Celsius. And again, these two things would be given to you on your formula sheet. All right, so 273 plus 23.9. And we get 273 plus 296.9. All right. Home stretch. All right, so number 21, ethanol, aka ethyl alcohol, has a density of 1.23 grams per mole at 25 degrees Celsius. If 80.1 grams of ethanol is needed for a reaction, what volume in mils should be added to the reaction container? All right, so this is how your density problem is gonna be worded. You're using density as a conversion factor in this problem. So in this density problem, this 25 degrees Celsius, just ignore it. The temperatures, I don't know why they added that, to throw you off, I guess. All right, so then our given is this 80.1 grams. All right. So we never want to start with a conversion factor because we don't know if we want it, what unit we want on top or bottom, right? So you always want to start with your given. So I want to determine how many mils, which is great because my conversion factor gives me the relationship between grams and mils. So I'm going to put grams on bottom, mils on top, because that's going to cancel my grams and give me my desired unit on top, which is what I want. That 1.23 is married to the grams, so it needs to go on bottom with the grams. So our final answer is going to be 80.1 divided by 1.23. And that's going to give me 65.1 mils. All right, 22, identify the number of sig figs. So, just a refresher, because again, we're going back to lecture 1. So leading zeros never count. Sandwich zeros always count. And trailing zeros sometimes count. And that sometimes is after a decimal and a non-zero digit. All right, so this first number has 2 non-zero digits, so we know that those are significant. It also has sandwich zeros, which are significant, so that means we have 4 significant digits. I'm going to write on top here 1, 2, 3, 4. That's our 4 significant digits. Our second number has a couple different zeros, so it definitely has 2 non-zero digits, but it also has 2 leading zeros. Oops, I'm just trying to highlight these first 2 zeros. There we go, which never count. But we also have a sandwich zero, which always counts. So leading zeros, they don't count. So I'm starting my count here. 1, 2, 3. That sandwich zero always counts. So this number has 3 sig figs.
So even if it's after the decimal, if it's a leading zero, it still will never count.
Correct. It has to be after a decimal and a non-zero digit.
Okay.
All right. So looking now at this number, so I have 2 non-zero digits. Those are definitely going to count. I have a sandwich zero. That's going to count. But now I have a trailing zero. This trailing zero is a question, it's a maybe, so it has to be after decimal. Nope, there's no decimal. It is after a non-zero digit, but it has to meet both of these criteria, and it does not. So this 0 is not significant. It would be 1, 2, 3. So this number also has 3 sig figs. All right. Our last digit, we have 3 non-zero digits. This digit, these 2 digits, this digit. Anytime you have times 10 to the third or times 10 to the anything, we don't calculate those in our sig figs. So we're only looking at this guy right here, 1.201. So we do have a 0 here, but it's a sandwich 0, which always counts. So that means all digits are significant for significant figures. Any questions? There's only one significant figure problem on the exam, and it's multiple choice. It says identify the number with 2 sig figs, something like that, and you're choosing A, B, C, or D. So not that I'd like encourage you not to study this, but if you're like still not getting it, I would study other things and try, if you're close on some other things, study up on those and just call this one a wash. I think sometimes studying is prioritizing things that you just know you don't have time to figure out. All right, last 2 on my practice exam here. All right, so I gave you a lot of different names here that we need to name. There's not this many on the exam, but this is one of them where I think there's at least 3, maybe 4. This one comes up a lot, so this is something that, I would put a little bit more of my time into, knowing that I have it down pat because you'll see it a couple different times. So the first thing with the naming a compound, remember there's 2 different naming conventions, and it depends on if a compound is covalent or ionic. So we need to figure out if it's covalent or ionic before we even try to name it, because that determines what naming rules we're going to use. So just a refresher, covalent, 2 nonmetals, and those are 2 objects that are on the right side of the periodic table on the right of that stair step. Ionic, a nonmetal and a metal. Non-metal. Uh-oh. Now my pen, there we go. Non-metal and metal. All right, so something on the left of the stair step, something on the right of the stair step. All right, so I'm just gonna first go through this list and determine if it's covalent or ionic.
Will this be on the reference sheet in the corner? The C is 2 nonmetals and I is a nonmetal and a metal.
No, this is something I want you to commit to memory. You'll get a periodic table, but you just need to know that covalent is 2 nonmetals, ionic is a metal and a nonmetal. All right, so covalent, okay, so nitrogen, oxygen, they're both to the right of that periodic table, so this is a covalent compound. Carbon and oxygen both are to the right, so covalent. Carbon and oxygen again, just in a different ratio, still covalent. H2O2, so we have to remember that hydrogen is like our one exception to the rule, like always, it loves to be difficult. Hydrogen is a nonmetal, even though it's it's on the left. If you ever look on like a color version, it's usually shaded the same color as the nonmetals, so this is a covalent compound. Magnesium and chloride, so magnesium's on the left and chloride is on the right, so this is ionic. Potassium chloride, also ionic. Potassium's on the left and chloride is on the right. So to name our covalent, we're naming using those prefixes. Right? So I would give you a table of the prefixes where 1 is mono, 2 is di, 3 is tri, so on and so forth. Again, I wish I could like have a million tabs open right now and like go back and forth, but hopefully you have your notes out in front of you and you're flipping to this slide. So I'm just using the prefix and naming what I see basically. So here I see that I have 2 nitrogens. So this is dinitrogen. And then I see I have 6 oxygens. 6 was hexa, right? Correct me if I'm wrong. Hexa? Yes, hexa. Hexa oxide. All right, carbon, or CO, sorry. CO, the first element is carbon. There's only one of them. This is like another exception to the rule. Chemistry loves their exceptions. So anytime an element, the first element of a covalent compound is singular, meaning mono, we leave it off. But this, if the second element is a mono, we leave it on. So you might think to yourself, this should be monocarbon, monoxide, but because mono is the first element, it's just carbon. So carbon monoxide. And I like to use this example of carbon monoxide because when you, it's a common, it's a term you've heard before. And you know carbon monoxide, you know carbon dioxide. You never say monocarbon, right? It's carbon monoxide, carbon dioxide. So I love to use this as examples for the mono rule, how you drop the mono on the first element, because you can think back to your real life. You've never heard it called monocarbon, right? All right, so carbon dioxide. I'm getting the di from the 2 on the second element. H2O2. All right, so dihydrogen dioxide. And you might have heard of this element before. So H2O, right? That's water. H2O2. This is like poisonous, deadly, I believe. I don't, dihydrogen dioxide. I think it has like a peroxide might be the like house. No, not peroxide. I don't know, I have to look it up. All right, now we're into the ionic. Ionic, we don't use the prefixes. Ionic's a little bit simpler. We just list them as we see them, making sure that we change the ending to "ide." So magnesium, chloride. I don't have to worry about the 2. Same with the KCl. It's just going to be potassium, chloride. Don't have to add any prefixes to ionic compounds. All right, last question. So, oh, what did I just do? So 24, what would be the chemical formula of Ca, calcium, and iodine? So this is an ionic formula. I know this because calcium is on the left side of the periodic table, iodine is over on the right. So I'm making an ionic compound. When I make those ionic compounds, I care about the charge. All right. I care about the charge, and I'm swapping those charges to make a neutral compound. So calcium has a +2 charge, and iodine has a -1 charge. So if I wanted to make a compound of calcium iodide, I need to swap these charges for its subscript. So calcium has a subscript of 1. I'll just leave that off. Iodine would have a subscript of 2. So the chemical formula for calcium and iodine mixed together would be calcium Ca iodide 2. CaI2.
What would it be if it was covalent? Like, how would you have to swap them or no?
Covalent goes by a different like you build molecules differently, and I just completely omitted that from our lecture because you don't have any of those examples on your test. You would have to go off of like how many valence electrons there are and like how to make a nice even perfect shell, and it's a little bit actually more complicated. All right, any questions?
So if it wasn't, if I didn't, if it wasn't -1 and say it was 3, I would just put calcium 3 and then I2.
So you're saying if this was 2 plus and this was 3 minus?
Yeah, or
Okay.
that.
Yeah, like hypothetically, then yeah, that would look like that.
Okay, okay.
How do you know that? Like, where do you get the 2
Yeah,
plus and -1?
I thought somebody might ask me that. All right, so that's the common ion trend where it's +1, +2, skip a few, +3, ±4, -3, -2, -1. So here's iodine, -1, here's calcium, +2.
And those numbers are not gonna be on the periodic table that you're gonna give us, right? Like, we're gonna have to know that order.
Yeah, so correct. So you'll get a periodic table, and yeah, you would need to know that. Usually what my students in the past do, that's as soon as they get the periodic table, they're writing +1, +2, +3, +4.
Okay.
So say I get one that's ±4, how would you determine if it's plus or minus?
Y- it's kind of depending. So it's like a minus if it's up here, and it's more of it's a plus if it's down here.
Okay.
It's where that stair step is right here. That's like the distinction.
Um,
But you won't get one that's this category.
okay.
All right. Anything else?
How long do we have until, like, how long is the test?
50 questions, and you have the entire time. I've seen people get done in like 30 minutes, and I've seen people take close to the full 2 hours. I would say average takes people about an hour.
Okay, how about like our lecture? Like, how's that gonna work next
Um,
week? Or this coming week?
so I've already covered the material that is in that lecture.
Oh, okay.
Yeah, so I went ahead and I think you were gone actually when I said this at the beginning of Wednesday. I went ahead and just like smushed everything into 3 lectures instead of spreading out over 4, or else I'd be like giving you a Zoom video to learn before this exam, right? I just went ahead and smushed.
Okay. Okay, makes sense.
Can we go over another balanced equation if you
Sure.
have any more practice rooms?
We'll just go to Google. I controls. All right, so okay, so let's do number 1 here. It's gonna be kind of messy because we got the other stuff. I'll go up. All right, so the first thing I like to write all the elements on each side. And then do initial count. So I have 3 hydrogens here. Plus I have also a hydrogen over here. So 3 plus 1 is 4. Then I have 1 potassium, 1 P. I have 4 O's plus another O here, so 5 O's. And 1 K, 1 potassium. Now I'm gonna do my initial count on the other side. All right, so 3 Ks. Yes, 1, 2, 3. 1 P. 5 O's. 2 hydrogens. All right, so I have 5 O's. I have 1 P. Those are balanced. I have a feeling that as I alter my other stuff, though, they're going to get unbalanced. Any particular place you want to start? I think I know where I want to start.
What
So,
was
no, actually go ahead.
would it be hydrogen
You want to start at hydrogen? Yeah.
or no?
I was
Okay.
actually thinking about hydrogen as well because, yeah, we can add a 2 here. That would give us 4. So then we have,
So everything is multiple choice, right?
yeah,
So it will give us like a few choices, maybe 4 choices, and we can kind of just plug it in and see which one fit. Like we won't have to just figure it out like this, basically.
yes, technically yes, because it's going to be like, it's going to have an equation that looks like this. This is actually a hard equation. We shouldn't have started this one. That's my bad. It's going to have an equation like this, and then it's going to say, okay, what's the coefficient for this compound? And then like ABC 1, 2, 3, 4 or something, you know.
Okay.
But actually, Michaela, do you mind if we actually let's jump down to 2?
Yeah,
'Cause
that's fine.
the more I'm looking at this first one, I'm like, wait a second, that's a tough one. All right, so we'll do our initial count. So we have K, B, and O are the elements we're working with. So 1 K on the left, 2 B's, 3 O's, 2 K's, 1 O, 1 B. Okay, so I see K and B by themselves, actually. So I'm thinking I don't want to start with a single element. I want to start with those oxygens because what I do, what I manipulate with those oxygens is going to manipulate the other elements. So I might as well start there. So if I throw a 3 here, I balance those oxygens, but it does increase my potassium here to 6. All right, so now my oxygens are balanced. But to go from 6 on this side, I can just throw a 6 in front of this K. That's nice. This, it looks like I'm not going to have to manipulate at all. It's going to have a coefficient of 1. And then if I throw a 2 on this B, it will get me balanced as well. So I believe there's two balancing equations. But like with anything that you're having trouble with, like I just did, I typed in, um, you know, practice balancing chemical equations. I chose this one because it showed it was a PDF, so I figured it probably had the answer key, which it does. So it's just a matter of, here's all sorts of practice for yourself, and you have the key. Also, I love this. I get a lot of worksheets or example problems from this Everett Community College. So if you ever come across one of those are always good ones.
Okay, thank you.
All right, any other questions to wrap up?
Can we go over density one more
Density?
time?
Yeah. Do you want to go over the same problem or do you want to go over a different one?
Different.
All right, so I'm just going to do the same thing I did. There's a PDF. Oh, it's already got the answers written. All right, here's one. All right, so number one, we didn't use this unit, but it works the same way. So don't freak out about it. All right, so here's our density. Right? 10.5 grams per centimeter cubed. We're finding the mass in grams. It doesn't state that, but that's the only, it should, because that's the only mass associated with this. That occupies 9.65 centimeters squared of space. So our conversion factor, our density, it's always something per something, right? That's a conversion factor, and we never want to start with that. We want to start with our given, which in this case is the 96.5 cubed, centimeters cubed. All right, so that's our given. Now we can use that density as a conversion factor to get to our grams, because this is giving us the relationship. All right, so I want to put my centimeters cubed on bottom because I want my centimeters cubed to cancel. And then I'm going to put my grams on top. All right, so 10.5 grams. And then it's just a matter of plugging this into our calculator. So we're multiplying this one, 96.5 times 10.5 divided by 1 is a large number. 10,132.5 grams. Now let's see if that matches their answer key. Oh yeah, they wrote in scientific notation though, and they did a little rounding. Any questions?
So for that one, we don't have to. So when it says find the mass, it's not like find the molar mass, right?
No, I wish
No.
this problem
Okay.
would have gave us the units because they should have wrote find the mass in grams.
Okay.
Your problem is that's the one thing that the test is written well is it doesn't like it tells you what unit it's looking for.
Okay.
All right, any other questions?
Can we go over, my bad, y'all. Can we go over the pH, the OH, that?
Mm-hmm.
I need to find-
So that's the problems we started with. So like, let me erase this. All right, problems like 1, 2, 3, or more problems like 4 and 5.
Problems like, what's that? What's one, two, three? Like once, what is? I don't know. What's that? Is this the same thing as like going from pH to H, or POH or
Yeah.
OH to POH, just the same?
Yeah, so this first problem,
Okay,
is OH.
to POH or no?
Nope, so this is H3O
Just
plus to OH.
okay.
This one is OH. No, sorry. This one is pH to OH. This one is what? H3O plus to pH.
I think on the second one, isn't
That-
it like you had to find the POH and then you
Yes,
Good.
this one was a two-stepper where we went from pH to POH because there's not a direct relationship here. So we did pH to POH and then we did POH to OH.
Okay, can we do that one? Really, all three if we got time, but
Well, it is already recorded.
okay.
But we also are going to do our lab on Tuesday is going to be all pH and POH, and there's like this giant grid where you have the pH and then you have to find the POH and the OH, and you have to do that for like 10 different compounds. So I also think that will really help cement some of this ideas, but I will still do number 2 for you, okay?
Is this gonna be on the exam? Any of
Yep.
these? Okay.
Yep, so all 3 of these are written like you would see them on the exams. I
Okay.
just put different numbers in here.
Okay, that makes I just wasn't here at the beginning, so I didn't.
Oh, yeah. Okay, that's fine, yeah. All right, so number 2. Actually, it's good that we're redoing this because I started the recording after I explained number 2. So you actually would have missed this in the recording, to be honest. All right, okay, so number 2. All right, so we have pH, right? We know that that's 3.34. We have, and we want to figure out what's the OH concentration. So let me find that acid base square so we can visualize this better. Some of these are ugly. Here's the one I think I have. All right, so we have pH and we're trying to get to OH. And like I said, there's not a direct relationship to get there. We have to do a two-stepper, which I think we all unanimously agree it's easier to do POH to pH and then pH OH to OH. So we're going to use this formula first. pH plus POH equals 14. And then we're going to use this formula. All right, 10 to the negative POH. So let's go back to this. Erase some of this. All right, so step 1, pH plus POH equals 14. So I have my pH plus X equals 14. Subtract each side to get X by itself. X equals 10.66. All right, so now I have my POH. All right, so secondly then, my second step, I will get to OH minus by doing 10 to the negative pH, or I'm sorry, POH. Let me rewrite this. To the negative POH, which in our case is 10 to the negative 10.66. So can somebody remind me what this was? Because this was one of them I didn't have pre-solved. So you would type in 10 to the negative 10.66 in your calculator.
That one is 2.18 times 10 to the power of negative 11.
Thank you. All right. Question?
No, that makes sense. Thank you.
Yeah.
Are we gonna have that
The square,
a
yes.
square?
Yes.
Okay.
All right, any other questions? How about I pull up this modified study guide and let's just run through it. All right, so from module 1 or lecture 1, we practiced identifying the numbers, we practiced using density. Oh, we did not practice this. All right, so if I had H2O, is that poly, tri, or diatomic, the entire molecule?
Would it be mono? Wait, you said poly?
Sorry, I
Would
heard
it be diatomic?
it's
No.
tri, so there's 2 hydrogens,
one.
1 oxygen, so that makes
Oh,
triatomic.
so you gotta add both.
Yeah. And then is it heteroatomic or homoatomic? Are all the molecules the same or different?
So hetero?
Different.
Hetero, right? So
Yeah.
you describe this, or you would choose the multiple choice that said triatomic, comma, heteroatomic.
Hetero means different, right?
Yes. All right. Define mass. I don't remember how I specifically defined it in our lecture, but right, the weight of something.
In a substance or object.
Yeah. All right, and convert from Kelvin to Fahrenheit. We did that. All right, determine if a property is physical or chemical. Do you remember what physical, like what? Well, yeah, I'll just describe it. So chemical is like chemically changing the object. That's chemical composition changes. Physical is like the 5 senses kind of change, like a color change, an odor change, something like that. So big things to point out. Chemical, common example is a bicycle rusting. That's chemical. Physical is changing like states of matter, so like ice melting. All right, so
In the book, it had described ice melting as chemically, I believe. And that kind of threw me off. I don't know why.
I'll go back and look at that, but it's definitely physical. Because your chemical composition doesn't change. It's still H2O. It's just solid versus liquid.
What would be another example of chemical?
Baking bread.
Right. Oh.
All right, so determine 7. We did that. We went from molecule. We did that one. That was our weird one where we had CH3H8, and then it was like 8 moles of hydrogen for every 1 mole of the entire compound. That was that guy. Okay, to be able to define the average atomic mass. So this is the average of all the isotopes. I believe that's almost verbatim how it's defined on the exam. Be able to go from molecules to moles. We did that. Know the properties of metals, nonmetals, and metalloids. So this is where we talked about metals are shiny. They're good at conducting heat. They are good at conducting electricity. We said that nonmetals are not good at conducting heat or electricity. They're dull. Things like sulfur and nitrogen usually come in like gas form. Metalloids have properties of that's between them. So kind of it's that those are the stuff on the stair step where kind of metals, kind of not metals. Okay. So we talked about this. 12, identify a element on the periodic table from its group and period numbers. I did not include an example of this one because we just kind of really seem to have gotten in lecture. That's when you say, oh, like the element is in group 2, period 3, and then you just kind of go do the little matrix and figure out what element that is. Be able to determine the common ion. We did do this when our very last problem where we figured out what the formula would be for that compound. So that was our very last problem where we did the formula. Oh, here's a good one. Determine the largest atom on a list. So atomic size, remember this is a periodic trend. So if this is our periodic table, size increases as we go down into the left. So if we were to have a list of elements and we're determining which is the largest, we want to find the element that's closest to this bottom left corner. 15, know the direction of the trend of ionization energy. It is the opposite of atomic size, where you're going up and to the right. 16, determine how many valence electrons are in an element. That's when we count just 1, 2, skip a few, 3, 4, 5, 6, 7, 8. Whew. All right, module 2. Calculate the molar mass. We did a practice like that. Go from moles to grams. We did a practice. Name. We did a practice of that. We did a practice of this one. This was our last problem. Know the difference between ionic and covalent. We talked about that. All right. This problem I gave to you basically in our lecture where I said know the difference. Okay. So know the difference is one part of it, and then knowing example is another part. And I told you the example is going to be glucose and water. All right, so I'm basically giving you a freebie on that one because it's a ridiculous example. I don't know how you would know that glucose and water is a exothermic reaction. So exo means it releases heat. And then endo means it requires heat. All right, be able to balance equation, we did that. Okay, so this we were kind of doing all along. We were knowing that the reaction was on the left side of the arrow and the products are on the right. We did not do an example of this, but this is our synthesis, decombustion, that kind of, not decombustion, sorry. Synthesis, decomposition, single replacement, double replacement. We did do an example of 10 and 11 on our practice. We did an example of 12. We did an example of 13 and 14. All right, so for module 3. All right, so this was our last slide that I gave you in lecture 3 notes. So be able to find oxidation and reduction. So oxidation is losing electrons and reduction is gaining. 2, be able to use solution terminology to imply it to the component. So it's like it'll say, okay, we have so many so many grams of sugar going into 100 mils of water. What is the solute? The solute is sugar. What is the solvent? The solvent is water. We did an example of this and this. All right, we did an example of the dilution equation. We identified acids. We wrote the conjugate. We did all this stuff in our practice, and we're going to do it in the lab. This, I just want you to remember that 0 to 6 is acidic. 7 is neutral. 8 to 14 is basic. 13, be able to define the use of a buffer and how it works in solutions. So this was like one of like our second to last slide, I think, maybe in lecture 3 notes. So a buffer just resists changes to major changes to the pH of a solution. That's all you got to know. You got to just pick that definition out of ABCD.
Can you say that again?
Yeah, so 13, you're defining what a buffer is, and the definitions are like A, B, C, D, and it gives you different definitions. And so a buffer, it resists major changes to the pH by using a weak acid, but resist major changes to pH. That's like the key there. And then 14, this was kind of a freebie that I gave you, but I'll give it to you again here. So dialysis, basically the question asked, what can't cross a dialysis membrane? Something like this. And the answer is colloids. Not that any of us really know what colloids are. So that's why I always give this question, because I'm like, what the heck is a colloid? Who knows?
And there's only one question about that, about dialysis.
Yeah.
Okay.
All right. I think we covered everything. I'll take any last questions. That's not the one.
Sorry, just one more thing.
Yeah.
I'm just still a little confused about that, like classifying the double replacement.
Mhm.
Like double replacement and those is like 4 or 5 of them. I like looked at the ones we did in class, but I don't know. I don't know. I don't get it.
Okay. Let me pull up an example. Well, this is interesting. Okay, let me share my screen again. Stupid ad. All right, so here, let's see if I can zoom in. All right, so I just went out and Googled, practice, classifying reaction practice, right? And so I found this little like quiz thing. I thought this was kind of cool. All right, so here we have one compound plus another compound yields a compound where they're joined together.
Mm-hmm.
So this is an example of a synthesis where two things come together, and you can think about people dating. All right, so synthesis. Let's see what our next example gives us is. Oh, do I have to hit the next arrow? Okay, this is a good one. All right, so we got a lot going on here. All right, so we have Ag plus NO3, but all of a sudden now NO3 and Ag are not together on the other side. We have potassium and phosphate, or PO4, but again, they're not together on the other side. They swapped partners. And swapping partners is an
Double.
example of double replacement. All right, let's see. We'll do maybe 1, 2 more.
Mm-hmm.
Okay, this one is, I'm just gonna tell you, this one's combustion. I kind of glossed over combustion because they're hard to identify, and I saw that it wasn't on the exam, so I was like, I'm just gonna gloss over this one. This one's combustion too. Okay, what do you think this one is, Andrea?
So we have the CA. It's now with another. Wait, hold on. Would that be the double replacement?
Yep.
Okay. I think I get that now.
Okay, you want to do one more?
Yeah. Um,
Okay. Oh, I don't like this one. Let's go to this one. Oh, this is a good one. Okay. So now they broke up. There was a couple and then they broke up into two different things.
And it's for like a for one like this, is it always gonna be two on the right side?
Correct.
Okay.
So
Okay.
synthesis is like 1 + 1 equals one thing over here.
Mm-hmm.
So this is synthesis. Decomposition is going to be like one thing and then it becomes two.
Okay.
All right, how do you feel now?
Yeah, I think I'm better.
And then single replacement, that would be the same thing and then like a new element.
Yeah, let's see if I can scroll through and it gives me an example of a single. Here's a single. All right, so we have calcium by itself. Calcium by itself. H is with Cl. Then all of a sudden, calcium was with Cl and H is by itself.
That would be a single replacement. Okay. So basically it's just looking for the other compound to be alone on the right side.
Yes.
Okay. Thank you.
Thank you. All right, so I'm gonna say for the last time, any more questions? All right, I'm gonna go ahead and end the meeting and I'll start processing that recording. It's a long recording, so it's gonna take a minute to like upload and for me to send the link.
Thank you.